For our senior design project, we created an automatic hydraulic test apparatus for RBC Sargent Aerospace and Defense. Sargent is a leader in the design and development of hydraulic locking actuators. Our design team will work with their engineers in order to design and fabricate an automatic hydraulic test apparatus, or AHTA, in order to fulfill their acceptance test procedure for their hydraulic locking shrink actuator. There are four main issues with their current test apparatus. Its large and redundant size makes it challenging to move to other pressure sources, and it consumes a large amount of space on the shop floor. The current test fixture puts technicians at risk when validating the ATP. There's an extensive amount of setup time as well as switching over time for left and right hand side testing. All their tests are currently being validated by the technicians, where we want the ATP to be validated also by our electronic system. Our mentor is Doug May. Our sponsors at Sargent are Tom Howard and Jeremy Ullman. Our team members consist of 3 mechanical engineers and 2 electrical and computer engineers: Jared Salomon, Evan Sheldon, Ryan Decker, Quinton Arnaud, and Spencer Kittredge. Our main objectives when creating this test fixture go as follows. We want to provide design concepts and improve Sargent's current test fixture. We want to analyze and justify these design concepts as well as the cost. We will then fabricate and assemble the AHTA, validate it at Sargent in order to validate their system requirements, and then provide Sargent with a fully functional AHTA by design day along with the technical data package. We approach this problem by splitting up the test apparatus into 3 main categories: the electronic design, hydraulic design, and structural design. Our approach to the electrical design is we wanted the technicians to be able to apply various inputs to the PC in order to validate the functionality of the shrink actuator. Then, the data acquisition system will record different parameters of the hydraulic circuit in order to validate the shrink actuator is working within the specifications of the ATP. For the hydraulic design, we wanted to redesign the hydraulic circuit as we found some redundancies, and we also wanted the hydraulic components to be designed for ease of use when operating the AHTA. For their structural design, one of the main issues we sought out was reducing the time it took for using the test apparatus. So we wanted our structure to be capable of switching between left and right hand variations in less than 5 minutes, because before it took them up to 6 hours to switch between left and right hand variations, with a total setup times of 15 minutes or less. Our structure will be built to withstand its internal loads and be resistant to cyclic fatigue from loading and unloading from external hydraulic power. The structure will be designed with safety factors of 3 and 5 and yield strength along with ultimate tensile strength. Our main technical system requirements are as follows. All required testing per Sargent's ATP. We want it to be fully adaptable for either configuration with a target setup time of 15 minutes, which is a great reduction from 6 hours. The whole apparatus shall be self-contained. We shall use Honeywell digital pressure gauges and transducers or equivalent. The data acquisition program shall be compatible with Daisy Lab, and we want an automated system to perform run-ins of the actuator. Our design concept was done using gantry-style cranes and lifts to design the AHT structure. Initially, our material was aluminum for weight reduction. However, we switched over to a structural steel in order to reduce fatigue from cyclic loading and ease of welding. Our point design graph can be seen here. This shows that we went over an airbag, deadlift, and teeter design. However, in the end, we ended up going with a deadlift design for ease of use and reliability. Our requirement verification shows our system requirements. For performance, we wanted it to be automatic, have rapid deployment, as well as being stable. For the environment, we wanted to keep an operational temperature of -40 degrees Celsius to 205 degrees Celsius. For the safety, we wanted safe operation by having an ergonomic work height, as well as an emergency shut-off that stops all activity in case the hydraulic pressure in any of the lines became too great. For the interface, we wanted sufficient electric power to all the necessary components, as well as sufficient hydraulic power to all the appropriate valves. for the design, we wanted a user interface that controls the test apparatus, a data acquisition system, and a data return system, again to an external PC with Daisy Lab. Our results were a little different from what we initially thought due to the quarantine. We weren't able to deliver a fully functional AHTA. However, what we could deliver was as follows. We are delivering an updated ATP with the new hydraulic and electronic circuit that we designed. We are giving Sargent any associated diagrams or operating instructions for our designed data acquisition system, which automatically takes all of the measured variables from the test apparatus to the actual PC. We will give them all our diagrams and designs for the improved fixture, as well as the main AHTA structure that is currently being fabricated by Cade Industries. And this structure can be seen here in 3 different figures. The main structure is shown on the left. In the center, you can see the structure with the load cell on it. And on the right, that is the completed structure with the data acquisition system and control box and everything on it. In the middle here, you can see this is actually where the shrink actuator will be placed. This is our hydraulic and electronic circuit that will be running the system. In black is the hydraulic circuit in which we created, and which we created and revised from Sargent. And in red you can see the electronic circuit that is controlling the hydraulic circuit with a Raspberry Pi and LED based control system. Some lessons learned was that we had to change materials for the structure after the design was complete in order to have a more stable system, and we also had to change out certain hydraulic components due to cost. Our project had very specific requirements, so we realized that we really needed to be efficient with our time in order to find reputable sources for high pressure hydraulic components. We also needed to create a structure that could house our equipment and meet ergonomical specifications. We also learned that it was very important to have a direct line of communication with frequent follow-ups for completing engineering projects as specific as this. Once the HT structure was complete, we wanted to build clear legs and guards based on structural geometry around the AHTA. We wanted our pressure-related hydraulic components to ensure that the hydraulic circuit can withstand the working pressures. And we wanted all moving components and pinch points within the load cell to be covered in order to prevent pinch and smash type injuries, as there's a lot of moving parts within our system. Some acknowledgements are Tom Howard and Jeremy Ullman, our sponsors. Ryan, the Sargent lab technician managing the current hydraulic test apparatus, as well as Tim Farley, who was a hydraulic component salesman. Here's our design day poster. We broke it up into the 3 main components of our design: the electronic circuit, the hydraulic circuit, and the structure. On the bottom left, you can see our completed electronic and hydraulic circuit meshed together. In the center, you can see our designed AHT structure. This is currently being fabricated by Cade Industries. And on the right is information about the hydraulic equipment in which we used in our system.